So this is still lesson 4.6, which is our review lesson. This problem was originally covered, I believe, in the homework in section 4.2. So polluted water is passed through a series of filters. Each filter removes, so that's important, removes 85% and the remaining impurities from the water. If you have 10 million particles of pollutant per gallon originally, how many filters would you need the water to be passed through to reduce the pollutants to below 400 particles per gallon? All right, so we have a bunch of useful information. We've got that we're removing 85%, that we're starting with 10 million particles, and we want to end up with 400 particles. So this is kind of like the car depreciation. Here we are losing 85%. So our rate, our R is negative 0.85. 85% is a decimal, but negative because we're losing. Formula for some percent change like this is your future amount is equal to your present amount times 1 plus your rate to the power t. So this is like the compound interest formula for yearly compounding. Our R is negative 0.85. So I need to know what is 1 minus 0.85. Double check on a calculator, but on a good day, I think that should be 15%. Okay. So then the next thing we need is our starting amount, and that's that 10 million here. We're starting with 10 million particles of pollutants per gallon. So, and that one is 400 particles. So I'm gonna have to write out 10 million here because this one is just 400. So my P is 10 with 1, 2, 3, 1, 2, 3, right? Because that would be thousands and then millions. Yep, so that's my P times 0.15 is what this 1 plus R reduced to the power T, and in this case, T is the number of filters. And I'm just going to say, oh, I called it F before. Yeah, we'll just go with that. In this case, the F is the remaining particles per gallon. Because that's what we're measuring, particles per gallon. So we want to know how many filters do we need to get it down to 400. So 400 is our goal. We have to solve for our power T. Whenever we solve equations, we get away things that are furthest first on that side. So the 10 million's got to go first. So we're going to divide both sides by 10 million. Good time for a calculator. On this side, the 10 millions cancel. And so we're left with just the 0.15 to the T. On the other side, we're going to get what? 0. A bunch of zeros. Let's double check 4 or 5 of them. Oops, I'm going to take 400. Oh, whoa, how did I do that? Ah, danger. 10, 1, 2, 3, 1, 2, 3. So Desmos is giving this to me in scientific notation. Thank you for that, Desmos. So we could either leave it like that, write it in scientific notation, or just do it the old-fashioned way, which I'm going to do. So I can divide by 100 top and bottom, and then I have a bunch of zeros in the bottom. I have 1, 2, 3, 4, 5 zeros. And so that's that negative 5th power. So down here, I'm going to need 1, 2, 3, 4, 5 places. The last place is the 4. So 0, 0, 0, 0, 4. So we need 4 zeros there. And that should match what Desmos said, which was 4 times 10 to the negative 5th. Anybody know what the next step is here? How do we get a power out of the power position?
Square root it?
That would only be if the power was a 2. Good guess, though.
Would you take the log of it?
Yeah, logarithms get the power down. So in this case, I want to do log on each side. So cleaning that up a little bit, we're stuck with the log of 0.00004. Make sure you have the right number of zeros there, or use the fraction. On the other side, the power comes down, and so that's my t, and we still have the log of 0.15. So the point of using the logarithm is that the logarithm pulls the power out as a multiple. So then we get the power times the log of the base. Last step is to break that multiplication right there. We divide by the log of 0.15. And so next we should hopefully agree on what the calculator version of this number on the left is. So let's do that. And I'm going to do it 2 ways just to double check. So back to my calculator. So I've got the log of 0.00004, if I got that right, divided by the log, and make sure you close your parentheses in the right spot, of 0.15. So I'm getting 5.33789, blah, blah, blah. If you were unsure about the decimals, then you could just leave our original fraction, which was 400 over 10 million. 1, 2, 3, 1, 2, 3. So just use the original fraction if you were in doubt, and then divide by the log of 1500ths. Yep, same answer. So I must have gotten the zeros right above. Now, this is the number of filters I need, and I can't, you know, just buy a third of a filter. Either I buy a whole filter or not. So in this case, I would round it up to 6, because if I only go with 5 filters, that's not going to get me where I need to be. So just to double check that, my original formula was 10 million times 0.15 raised to the number of filters. If I only use 5 filters, then I'm now down to 760 particles per million, which isn't close enough to the 400. If I jump to 6 filters, so I take my 10 million times that base, 1500ths, but this time raised to the 6th power, now I have it below 400 particles per million. So I got to go with 6 filters, not 5. Okay, so this isn't a straightforward rounding. We got to go with 6. So again, this cancels, leaving t is about 5.34. Since these are filters, I'm going to have to round up, otherwise I'm not filtering good enough. All right, questions on that?